Hi everyone. Pleasure that some of you came again. But yeah, everything is recorded as you can see. So this is the second day of our workshop in our little event. And today is a lot more workshop focused and a lot more kind of you guys actually doing things. The first set of speakers is two brothers, but I'll introduce the first one, David. So David is today going to talk to you guys about some ABCD matrices and matrices and efficient design and simulation of distributed microcircuits. David himself has studied at ETH Zurich in his undergrad, where he did some stellar research for Pahl as well, and but not yeah. Just need to remind myself. And he has done some stellar research for Pahl there, and then moved to MIT to now work with Will Oliver, where they are working on numerous things. One set is these things, but also QDW codes. They're wonderful researchers, and you'll have them for 3 hours. And if you have any questions, feel free to ask. Online, same thing. If you have any questions, please don't hesitate. And with that, let's start the day. And welcome our speaker.
I'm excited to be here. Like Nick said, I'm with Will Oliver. He would have originally been here, but I'm happy to be here in his stead and also expand a little on what my research is. Really excited to give you hands-on tools to design devices just like I do and I have done. And in the workshop later on, you'll use those tools. So looking forward to that. Let me just start dive right in by showing you a device that I made that has 9 qubits. For academic scales, this can be considered medium to large scale. And you can see there's a lot going on, right? We zoom into one of these places, we can identify a qubit, right? And you can see that it has lots of capacitances. It's coupled to other lines. Generally, it seems really complicated to think about, right? Let's look at a different point. Here we are looking at 2 qubits that are coupled together. And similarly, we can model this using the circuit abstraction where we use inductances, capacitances, and transmission lines, these things over here, to model all the different subcomponents in our device. Let's look at one more place. This would be one of the readout resonators. Again, you have lots of transmission lines, capacitances, and transition lines. And really what I want to convey to you today is that if we understand really well how to model this using a circuit abstraction like this, then we can design devices. And I want to explain how to do that. And so kind of the guiding theme of my talk is that layer, this schematic layer that mediates between the actual layout of the device and what it's supposed to be doing, which I abstractly call here like an input-output model in this case, or abstractly, if we think about our device, what the speakers have been highlighting, a quantum device really is just a lot of modes that are coupled together, right? And so this here, it sort of mediates between that layer and this layer. And the added advantage of this thing is that it also captures distributed physics, like different speakers, Devray and Michelle and Zlatko mentioned. Often we ignore the fact that in our layout we have long lines that are more accurately captured by transmission lines. We'll not do that, right? We'll take these into account for more accurate modeling. Right, and this layer is computationally efficient. So a big theme of this workshop is how do we make design and simulation faster and easier? And this may be part of an answer. So I'll introduce you this ABCD basics, this formalism, and then we'll apply it to designing readout circuits, and then to a qubit coupler, in this case, one that's very long range. And before I do that, I want to show you sort of the Bible of this whole discussion. It's this book. I recommend you all to wish for it for next Christmas and study it thoroughly because it explains all of classical microwave engineering. This includes electromagnetic theory, transition line theory, all that good stuff that we need in practice to build superconducting qubits. It's essential but complicated, and we'll touch on a few of these aspects today: transition lines, resonators, and so on. Let's dive right in. So if we take a cutout of our chip, what it actually looks like is this. We have a thin layer of metal deposited on a superconducting metal, obviously deposited on a substrate. And typically we have ground planes that are surrounding our signal plane. So they're all on the same layer. And what this causes is that the fields, they sort of distribute in a coplanar fashion. They go to the sides. And then specifically those transmission lines, they also have a length and extent, right? And the physics that happens in these, geometric elements can be abstracted with this model that I've been showing a lot, the transmission line, right? And it models traveling electric fields and waves. And we'll see later how it can be efficiently capture everything that's going on in this layout. I have some data to back up my claims. Using just a few parameters, there's this notion of a phase velocity, we'll call it VP, which is essentially, it tells you how fast light or the electromagnetic wave moves through this line, right? So the fastest it can be is speed of light, but because this electromagnetic wave also penetrates into not just vacuum, but a sort of more a slower medium, silicon, it's slowed down by an effective dielectric constant. So it'll be some fraction of speed of light, maybe half or so, something like that, a third. Then there's also a characteristic impedance, which we also need. And it can be characterized as the inductance per length divided by the capacitance length squared. This is something you can also retrieve from solving this geometry. We won't do that now, but there's these two parameters, and then there's also the length. All of this describes the complicated behavior. And so really the claim is we don't have to solve this all the time. If we just know these three parameters, and if our structures are standardized and not weird, then we can just use this, and it's faster. So in general, a complicated device has a lot of electric waves going in and out, voltage waves and current waves in our case. We can model it as an N-port network. And there's all these inputs and outputs. And you've seen maybe yesterday already these S parameters. These S parameters, they basically relate input and output voltages to each other. They're very important because they allow you to do things like readout and characterize your device. So one S parameter effectively is just, Sij is just the voltage going in at port I divided by the voltage going out at port J. This should be J. And now comes the crucial part, and I need you to pay attention at this point. So I said we have N-port networks in general. What if we just had a two-port network? So a network that only has one input and one output, nothing else. This is often the case, like our readout circuits. So if you have one point where a signal goes in, and then one point where it goes out. In that case, your network can be efficiently described by a concatenation of ABCD matrices. So what these do is they describe the input and output relations of the input and output voltage and currents. But more importantly, they do that in a way that you can just multiply them together to get the ABCD matrix of the whole thing. Okay, so one ABCD matrix describes part of your network, and these different parts, you can just multiply these matrices together, and they describe the whole network. And then what's really cool is there's a very simple transformation. You just take these four numbers, and you plug them into this formula, and you get your S parameter. In this case, this is the formula for the S21 parameter, right? And this is, for instance, something we rely heavily on for designing readout circuits. It's efficient because it just relies on matrix multiplications. there's an assumption here that the subcircuits don't have crosstalk to each other. So really the guiding principle is that ABCD matrices only work if you understand your layout and your system well, if you have standard components and there's not a lot of crosstalk. You can model that crosstalk if you know how to model it, but their main strength is the computational efficiency. Yep.
Quick question. Do the ports have to be connected in some way for us to be able to multiply, like in series or?
Yeah, so they have to be connected in series, and we'll work through some examples later on. It'll be clearer when we show some examples. But principally, all these ABCD networks are just series concatenations of each other. But we'll see how to make more complicated network topologies. So let's look at some of these ABCD matrices. Say you have a series of impedance, then the ABCD matrix for this is 1Z, 0, 1. And that impedance can be, for instance, a capacitance or an inductance, series capacitance and inductance, of which the impedance is given here. I'm sure some of you are familiar with these circuit elements and their impedances. Let's look at some other examples. So if there's something that's parallel, going to your question, so this might still be in series, to another ABCD matrix, but if your element goes down to ground, and say it's a capacitance or inductance, you put its admittance here in 1, 0, Y1 in this form. And then my favorite ABCD matrix, and I hope it's your favorite too, is this one. This describes a transmission line. And I really want to, just spend some time here acknowledging the fact that we have a 4-entry matrix that can describe the complicated electromagnetics in an arbitrarily long full-planar wave transmission line. That's really where a lot of the power of this tool comes from. Let's look at an example of how to really construct the ABCD matrix. So let's say you have this circuit and you want to find the transmission from 1 to 2. So what you can do is you can, this corresponds to a layout maybe in reality, and you could just throw that layout through some complicated electromagnetic solver, but that'll take a while. Alternatively, you can find the ABCD matrix of each of these subcomponents here, and you can really see that they are concatenations of each other, just concatenations. And then you just multiply them together, and I won't show it explicitly here, but you get some full ABCD matrix. And then you just use that formula for S21, and you maybe simulate for different values of the frequency, and you're done. You got your transmission spectrum. There's one more ABCD matrix that I want to show that's really useful. Often in our circuits, we have something that's hanging off of a feed line. Like maybe you have a feed line, and then you have like a resonator or something. You can make a more complicated transformation where you just take an arbitrary ABCD matrix, can describe something that's more involved, like what we just saw. But if this were in a hanger configuration, so like if what we just saw was actually hanging off a feed line and shorted at the other end, then we just take its ABCD matrix, the one we just computed, and we realize that the input admittance going through here is just D over B. So you just take D over B of that matrix. And then having that input admittance, we can use this one that we already introduced and say the total ABCD matrix of this thing is just 1, 0, D over B, 1. So that was a little fast. Don't worry, we'll have exercises on this later. But again, if you have some arbitrarily complex two-port network and you have its ABCD matrix, you can transform that into this hanger geometry by just putting its D over B, just writing this matrix down, 1, 0, D over B, 1. Okay. Pause here. Yeah.
Like in practice, we'll just have like a lookup table to this ABCD matrix,
yeah.
Or should it be obvious to me
why these transformations hold? Yeah, I'm not going through them in detail because yeah, it's just some algebra you can do. There's in that book Posar, it's all in there, right? And in fact, there is a lookup table in there, right? So And I've compressed it here. So these are the important ones. These are the only ones we'll need to design all the circuits that I, for instance, have designed. So let's use these and actually build some circuits, and let me simulate their transmission. So maybe some of you are familiar with what this is. This is an LC resonator that's capacitively coupled to a feed line in a hanger configuration, right? So if your signal goes in here, it can couple to your LC oscillator, and then it couples out again and goes to port 2. And at resonance, you get a strong feature here. And this resonance is set by the formula many of us probably know for an LC oscillator. Just, yeah. I want to note that this is loaded by the capacitance, like has also been discussed. So this coupling capacitance also shifts it, but roughly we can really see that our simulation produces what we expect. Now it gets interesting. We can start to simulate some distributed physics. So now I'm making a quarter wave resonator. So this is our first really distributed element we're looking at. We have a coupling capacitance, and then we have a piece of transmission line that ends in a short, right? So how did I construct this? I first made a series capacitance and transmission line. I got that ABCD matrix, and then I used that hanger transform, right? That's it. And you can see just that, and then simulating it for different frequencies gives something very striking. Higher harmonics. This is also what we expect. I mean, assuming some of you know how these, resonators, distributed resonators work, there are waves that can fit in here, and multiples of that fundamental wavelength all resonate, right? And that's what we observe. And we can also confirm our intuition using the formula. This is the formula for all the N resonances in a quarter wave resonator. LR is just the length of this thing. And we can see that they line up. In fact, later in the exercise, you'll build this exact circuit and see that it agrees with this calculation. You can do it yourself. And there's one more distributed circuit that I want to show. It's this one here, where you have basically the same, but now you have a capacitance at the end. So this is no longer a quarter wave resonator, but it's a half wave resonator. So what this means is the fundamental mode is one that's where the wavelength, where this length here corresponds to half a wavelength. And this is set by these boundary conditions here, right? Both open means half a wavelength fits in here, and that's the mode that will resonate. Okay. What's interesting is to make these two have the same fundamental frequency, this one needs to be twice as long as that one. And as a result of that, you have twice as many modes. You can confirm this just by using this formula. This is the formula for the N harmonic, all of the N frequencies in a half-wave resonator. And you can confirm what I just said by using this formula and comparing it to that one. So in practice, we want to do this, right? All those circuit quantization methods, they all assume something like this. But it's easiest to just build this, right? This is a very simple structure, and it's very easy to build accurately. And but we have these higher harmonics, right? Are they a problem for us? They can be, right? And so that's why we want to simulate this. But in principle, we rely on the fundamental mode here to approximate this. So often we just pretend that these aren't even there. In essence, yeah, we want to approximate this. Okay, now I want to talk.
Yeah, just for the orange case question, the value of the bottom, doesn't the capacitance affect its response?
Exactly. That's a great question and a great segue to my next slide, which is, like I said, these resonators are loaded by the coupling capacitances, and we'll see the effect of this now. So there's some algebra you can do, and I'm happy to walk through it with you if you want to. I don't recommend you to, but I can do it. And it proves, or it shows that a coupling capacitance here effectively loads and adds effective length to your resonator. So capacitance sort of makes the resonator look like it's longer. and by VP, by the phase velocity times the characteristic impedance times the capacitance. That's roughly the formula. This is an approximation, but it holds pretty well in practice, and we'll see how well. Okay. Now,
Does the CPW gap and thickness affect the capacitance?
for sure, the CPW gap and thickness, so the thickness doesn't really affect it because it's really thin, so we can almost approximate the whole thing as perfectly thin. The gap to the ground sides does affect, if your ground is really far away, that reduces your capacitance. It's closer, it increases the capacitance. So this shape here, this sets CC, but we can simulate this, and we will in just about a second. And in fact, this also is a good segue into how do we actually model the capacitance. So in reality, we're getting a little more exact here, is these capacitances also change how much there is, they also add effective capacitances to ground at the terminations here. Okay, and we'll see that it's really important to include these. And just like CC, the coupling capacitance, it contributes to your effective length. It also increases the effective length of your resonator. So how do we simulate that ground capacitance? Say we want to, we want to use this coupler shape here, and we want to know what that capacitance to ground is. So what we would do is we would create a model that looks like this. It's terminated with an open on both ends. Unfortunately, you can't really see the ground plane and cutout, but you just have to trust me that there's ground around here. So you mirror it, and then you also have a through line that's the same length. So what this effectively corresponds to is here you have roughly to this circuit here. You have a transition line that has a coupling capacitance across, and these transition lines, you can also treat them just as pure capacitance to ground for our purposes. We perform a DC simulation later on, where treating a piece of metal, no matter how long it is, you can say that that's just capacitance to ground. There are no distributed effects. So effectively, we get the capacitance to ground of this line piece here and here. And this through line also has some total capacitance to ground. And now how we get these things, these capacitance to ground that I showed you earlier, is we introduce this notion of a reference plane. Just bear with me, it's just normally just aligned through the middle of your coupling capacitor. And then what you do is you perform this simple calculation. You get this coupling capacitance that you found here, and you subtract from it the through line divided by 2. So what is that effectively doing? What that is effectively doing is you're saying, what's the difference in ground capacitance that this weird coupler shape provides compared to just a normal CPW that goes right up to the reference plane, right? If you just had CPW going right up to the reference plane, you probably would have less capacitance to ground. But since these things kind of extrude to the side, they add a little capacitance to ground at this point. And if you follow this procedure, you can sort of make this nice thing where you can treat this model here, this layout piece, as this capacitive network. And you can say that a transmission line that leads up to this, this capacitor, it just starts to its left, and it can go arbitrarily long. Like what I'm saying is this approach here in general allows you to sort of treat this whole thing as a module that you can plug and play into networks, because now you know how to, take it out of that network. And it's just this simple thing here.
Yeah, question from the online audience. The slide seems to be not clear, at least the transition to the previous slide, like how are they related?
So they're related by, we're looking at how capacitance loads a resonator. And now we're looking at how to get that capacitance from an actual shape, right? So a layout of an actual resonator will have a coupling capacitor with a certain shape, and we're looking at how to get this ground capacitance, right? because it does affect our resonance. And we'll see how. Yep.
So C-through is the capacitance that you have if you just took a full length transmission line divided by two, right? CPW is what you would have for the actual length of your, right?
Well, so
Is that right?
it's kind of correct, yes, but in this case here, we're ignoring how long the resonator actually is, and we're just doing a little simulation to extract the capacitive network of our coupler. And we can do this independently of how long our resonator ends up being. And this toy simulation that we're doing is we add some length here. It doesn't have to be exactly the resonator length. We want this to work for any length of resonator. And we just have, yeah, you just follow this recipe where you have some length and it's terminated with an open, and then you have a through line that it just goes through. And then you described correctly, the capacitances are just the capacitance of this piece of metal to ground, and CCPW is this piece to ground. And then,
So like intuitively, you expect actually CPW to be larger than C-through over two because of the extra pad that give you more.
exactly. And that correction is quantified here. That's the correction. That's how much more capacitance to ground this shape gives compared to a CPW that goes all the way up to the reference plane, right? And that's if you take the capacitance of C through total here divided by 2, that counts the capacitance of this thing up to the reference plane, right? The reason why we do this thing divided by 2 is to take care of fringe effects, and I can talk more in detail about that later. Just want to give you the recipe here now. This is how we treat and how we kind of take out the coupling capacitance and you know, make it something that's modular that we can plug and play with our networks. And this is very important. Yeah.
Question from online. That CCPW is a total capacitance of the transmission line question. Is it the same as capacitance per unit length times the length of the CPW?
It is for the see-through, more or less, because that is really a well-defined CPW. But CCPW, maybe I should have chosen a different word, includes, you know, the capacitive contribution from this extruded part here. So it's a little more than just CCPW times that length, or the capacitance per length times its length. So now I want to convince you that this actually works. I just want to show you how would we plug and play this into a network. So say we have a hanger transmission line or a hanger resonator, and we zoom in again. Really, how you translate this layout to an ABCD network or a microwave network is you count the length from here all the way to the reference plane. And then you take the coupling capacitance across that you simulated and the coupling capacitance to ground on both sides that you just extracted. This is how you would simulate this network. And then the transition line going up, you have to count its length starting from the reference plane going up. Right? That's how you do this accurately. And what's also cool about this approach is what we can do now is we can just repeat that simulation for different sizes. So now we just sweep the size of your coupler and just you repeat this whole analysis. And now what you get is a lookup table, a direct map between capacitances and their capacitances to ground to a size. And so now if you're someone says, hey, I need a coupling capacitance that's this large, you can immediately give them a layout and you know how to correct for the capacitance to ground. So it's directly plug and play, right? You can directly do this and you don't have to play around and do like loops and try to hit it and then be surprised by, oh, there's a capacitance to ground correction. You've already taken it into account. Yep.
How did you get CC from this?
So yeah, you do a full Maxwell simulation. So that's just a full capacitive simulation. It gives you the entire capacitive network. And that's just the capacitance from all the potentials to each other. So I've talked a lot about the two sides to ground, but you also get the capacitance across. And that one you can just use like that. You just take the capacitance across, and that's the one you use. Right, and this lookup table, this makes also the design process a lot faster. If we now know we need to make capacitance, we know how to make it big and accurate. And that's what I did. So here's a test device with slightly modified shape of capacitance. This one is asymmetric, but you can use the same principles to extract capacitance to ground on each side. Remember that what affects the resonance frequency to first degree is mostly the capacitance across and the capacitance ground that's on the resonator side. So I'm drawing those here. And we've extracted them using the same methods as before by introducing a reference plane here, in this gap, and so on. And these are the resonance frequencies that I've measured. And now I want to show you, if we use this formula, but we neglect both of these terms, then we get the red dots. And you can see they're over gigahertz away. It's a big correction. And now if we include the capacitance across, the one that most people can easily do, it already gets a little better, right? But this is still way off. You can't design a device like this. And if we now include the capacitance to ground, the blue dots disappear. And this is just really data out of the box. And it shows that this capacitance to ground correction is crucial. And what's really cool is having done that, also simulation against size, I can lay out this whole device here, and I don't perform one EM simulation, and I get this targeting accuracy. Right, and that's how much faster your resonator design can get. Okay, so I'll rest there and see if there are questions. Camera's looking away. I don't know why it's doing that. Maybe it'll come back. But I hope the screen is shared. So now I want to continue, and I want to talk about not just yet.
Just to confirm, you still derive CC via simulations, right?
Yes, everything is derived by simulation. Yeah.
Okay. You can calculate CGR just by hand?
No, I calculate, so I derive a few other capacitances also via simulation, and then I can calculate them together. Okay, so I can use them to calculate what CGR is, right? Also note that in this case, I varied the size of my couplers. So also showing here that this works across different sizes of couplers, different magnitudes of capacitance to ground, which is also why you have the stepping thing. I use two different sizes of capacitive couplers, but both times the corrections are accurate. Yeah, the camera's doing weird
It's pointing at me. It's pointing at me.
Where's you and me? All right, we've talked a lot about where the frequencies of our resonators land. If we zoom into one of these resonances that so far look more like lines and dots, we see a Lorentzian line shape that goes down and up and has a certain width. And this width here refers to this line width, kappa. We're also interested in accurately getting that, right? Not just the resonance frequency. You have a question?
Yeah, so we're kind of modeling this, what we want to be an LC circuit hanging off a transmission line as a resonator right here.
Yeah.
In this picture, why does that have any inductance?
Yeah, so it has sort of inductance, or yeah, it looks like an LC circuit because of its distributed nature. I can give different answers to you, but one of them is being the frequency at which this resonates, 5 gigahertz, that has a wavelength, right? That corresponds to a wave that's distributed in space. And that wavelength fits snugly into this resonator, or a fourth of that wavelength fits snugly into this resonator, causing that wavelength to be trapped, to resonate, right? That causes all this behavior. And that is sort of, that's very different physics than, an LC circuit where you have inductance. But you can say that, this distributed nature contributes inductive effects that cause, something to resonate. If a network was purely capacitive, it would not resonate at all, right? So my most accurate answer is the best way to think about it is if you think about the wavelength that fits into this piece of line.
Yeah. So I'll ask you first, can you go to the camera and wave with your hand? Just go in front of it.
How close?
And then
It's
Yeah,
blue now.
no, go right, yeah, go right. Okay, I'm gonna leave. Because it's fixed on me for some.
Okay. Do you want to continue?
Go get in the camera, wave at it. And yeah, it's gonna be blue.
Yeah, there you go.
Oh, I think it got me.
Yeah, now I
All
follow.
right.
Perfect, cool.
All right. So I want to say, yeah, when we zoom into this. You should just stand here.
I go to the other side. Yeah, very good.
Little sabotaging my presentation. Okay, this is better. Okay, so we've generated this trace using an S21 using our ABCD matrix formalism, and we've gone really close. Now we can fit an analytic function to this thing, and it looks like this, and it's parameterized in kappa and frequency, resonance frequency. So you can see the fit is overlaid here and dashed. And from that fit, we can extract what the actual line width is of this thing and the resonance frequency, right? And later I'll show data that also confirms we're able to target the line widths pretty well. Okay. I want to introduce a few more notions here. One is this, you have a question?
Yeah, is the Z port same as the characteristic impedance?
The Z port.
Yeah, the Z underscore port.
Oh, yeah, that's the characteristic impedance that we assume at the ports here and here. So there's a characteristic impedance associated with these ports. It's part of this formula.
And another question, does CGR grow faster than CC, especially if you're on a size of 30 to 40 units?
It depends on the shape of your coupler. Yeah, most often I found that to be true, but it really depends on the shape of your coupler. Yeah. Okay. So this formula here is only accurate if your resonator is coupled to a perfectly matched feed line. So something like I showed on the previous slide. So if there's nothing else here, if there are no impedance mismatches on this line, then our Lorentz will always look perfectly symmetric. Now, if there are impedance mismatches on here, that'll introduce asymmetry into your Lorentzian. It'll look weird. I'll show some plots. And we can extend our model by this thing here, a parameter phi, which introduces this asymmetry, a phase roll. Now, if we use this to fit our functions, and let me also show this thing here, we see the fits are really accurate. They work well. Okay, they overlap nicely, and you can see this asymmetry here. You can see that this arises at different points here. We also recover one place where it's nice and symmetric, but there's asymmetry. Now, what's going on over here? Here, you can see that when we fit this line shape and extract kappa, and we plot it while sweeping the position where this resonator couples, your kappa goes really down and up. And this is simulation data. This is not numerical, like not analytical. This is just a simulation. It goes up and down like a cosine. So what's happening here is, and let me take a step back and say what actually happened. Let's trace back a few photons as they travel through this circuit. When a photon is resonant with your resonator and it's traveling here, it goes in, right? So we're starting with a scenario where a resonator has photons, right? They're reading out your qubit. Now we'll follow them on their journey back to your computer. So when they couple back to the feed line, they scatter bidirectionally. So half goes to the left, half goes to the right. Now, the rightwards traveling photons, they just go to your port and up, and they're part of the information you retrieve. If this capacitance here weren't there, then this other half would be lost. And in fact, this would reduce your collection efficiency or your quantum efficiency. In other words, it would reduce your signal to noise ratio. So often we put a capacitance here such that the photons that couple and go to the left, they actually, when they reach here, they are reflected back, and this is almost a perfect reflective boundary, and then they also travel to the right. And now you get all of your photons going back up. What this does, though, is now you have two groups of photons, and they have a relative phase to each other, right? With each meter, or each distance unit of distance that they travel, they acquire a certain phase, and if those relative phases are different by, then if there's, for example, difference by pi, then they interfere destructively, perfectly, and they cancel. And then actually, you see what you recover here. There's no coupling. Those photons look like they never left the resonator because they destructively interfered at this point. And then there's the other points of constructive interference, right? And this is what reconstructs this thing. And if you plot this phi parameter, you also see that it wraps between minus pi half and pi half. Doesn't mean a whole lot right now, but we will use it for designing readout resonators. Okay.
Quick question, just do the photons in the blue line then also get reflected by the capacitor there instead of coming back in the,
Here.
yeah,
Yeah, and I think that's what that is. That's
You want
captured
that?
in the finite value of the line width here. Basically, this thing is a little bit transmissive, but not perfectly, and
Yeah.
the rate at which it is transmissive sort of is that that line width. Yeah. Okay. Now also to at least qualitatively prove, yeah, so we can see there's this interference pattern, and what we use this for in practice is to increase quantum efficiency. And at least qualitatively, and later we'll also see that the line widths line up nicely. We can see I created this device here that looks like this. We have an input capacitor, and then we have lots of resonators, and we just fit their line widths, and sort of we're doing this sweep along the feed line in hardware, and we can see this behavior.
Yeah, there was a question, I'm not sure. Why did we simulate at 5,000 gigahertz center frequency? Or was it 5?
Maybe that's a typo. That's a typo.
Yeah, that's a typo.
That would be some distinctive. Yep. Okay, so that's my last. There's one more piece of evidence. People often ask, can these ABCD matrices also capture air bridges? Yes, they can. And so air bridges are these things that you use to put around CPWs, and they just provide good ground. They connect all the ground planes. Like Michelle said yesterday, there's no such thing like a perfect ground in RF. What you really want is that they're coupled together, right? So apparently I'm using the symbol that's actually used for washing machines, laundry machines. It's not the right one, but everyone is, so I don't feel bad. Anyway, we use these air bridges and we just model them as a capacitance to ground. What we try to do is we build this in simulation using like sheets and whatever in 3D, and we extract roughly a capacitance of 1 femtofarad. And then what we do is if we have a big, a full device, we just literally place these air bridges at their respective locations. So we interrupt our transition line. And this is a very small capacitance, so it's a very small interruption. Doesn't really change the physics a lot. What it does, though, it does shift your resonance frequencies. Again, if you're adding capacitance to a resonator, it shifts the frequency of your resonator, shifts it to lower. It increases the effective length. And so what I did here is now I just have resonators with air bridges on them, and I measure these frequencies. And now if I model the whole thing and use my formula, or if I just model them in ABCD and look at the frequencies that I get, they're a little offset. But if I now include air bridges and I tune the air bridge capacitance until these dots align, so here I'm tuning the capacitance until the dots align, roughly, then we get something like 1.2 femtofarads. What's nice is that the fact that this value is close to the one we simulated shows that we're kind of capturing the same physics here. What I want to say is that air bridges have weird shapes, and so it's hard to build it exactly in simulation. So the best value to use in future designs, which I also do, is just to use the one that you extracted experimentally. So taking a lot of time here to get the basics, and I'm for sure will not get through all of my slides, but I do want to take a moment here before we segue. Yeah.
Can you speak on the effects of chip-to-care PCB wire bonding and resonant frequency transmission?
Yes, for sure. So wire bonds, does everyone know what wire bonds are? So what they are is the signal that doesn't just end here on this pad. In fact, in reality, this chip is embedded in a PCB that has a cutout where this chip fits in. And then there's a piece of metal, a wire that sticks to this pad and then sticks to the CPW on your surrounding PCB. And that piece of metal actually adds inductance. So it looks like series inductance. And the effect can also alter your physics in your device. So you want to simulate them too. I also have test devices that do that. I won't talk about them here.
And a follow-up, does the distance between air bridges affect the capacitance?
Between air bridges?
Yeah.
So what definitely affects capacitance is how tall the air bridges are. So how big this gap is. If this is very high, then the capacitance is low. Between air bridges shouldn't affect the capacitance. Okay, someone wants to get that probably. Okay, so I have you for 3 hours, so I might as well take my time. We'll see how far we get into this thing. So now we've introduced all the basics. This is everything basically that I know. It's everything you need to know to design readout circuits accurately, surprisingly. And that's what's really cool. They look like this. And I'll segue first by taking a break from all this distributed stuff and talk about just resonators, blunt resonators.
Before you do that, can wire bonds make impedance matching between PCB and chips worse?
For sure. Okay, dispersive readout.
Just a logistics question. Do you have your slides somewhere?
Yes,
That I can-
they're on the drive.
Okay,
So
cool.
I'm pointing to Nick.
I'll send it.
Thank you.
But yeah. So yes, if I don't make it through all of them, homework is to go through all of them.
You'll get all the stuff, by the way. We're uploading the videos right now. Everything is done there.
So at this point, you've probably heard like 15 times how it works. So does anyone want to explain dispersive readout? I'll do it. So the way you do it is you couple a qubit to a resonator. And in this case, I'll show it in the hanger geometry because that's the one we're using. So we have a feed line that goes across here. And if we look into the ports, the transmission from left to right, then we see that Lorentzian resonance, right? I'm showing here though how that resonance shifts depending on the qubit state, right? Now, if we center a drive, for instance, between these two or on one of these dips, in this case, that looks like a good idea, then there will be no signal going out if your qubit is in ground, and there's a lot of signal going out if your qubit is in the excited state. And this difference you can use to determine whether your qubit was in the ground or excited state. So what we do is we just send a frequency, a pulse at, say, this frequency here, and then you integrate that signal for a certain duration, and that number will be very different depending on if your qubit was in the ground or excited state. That number ends up looking like a blob. This is if you take many repeated rounds, many repeated shots, they end up somewhere in a circle because of noise, but they are different because of this fact here in the middle. And this separation between them, you can sort of introduce a threshold somewhere here and say, okay, if the number that I got from my single shot was above this threshold, you're in the ground state. If it's below, you're in the excited state. That's it. Right, oversimplified, but that's also a really good place
So
to.
it's just a frequency sweep, like you guys kind of just guess based on where you think you should put it and then you just sweep it, like.
So the readout pulse stays constant at one frequency.
Right, but then like
Yeah.
every shot you like sweep it till you find the other one?
No, you keep here, every data point was produced by doing the same pulse at one frequency point. But
At the center.
center, or I just like in this place here, it makes sense to put it on one of the dips because you can see there's a big contrast between the transmission.
I guess what I'm asking is, imagine you didn't know where the dip was.
Oh, to get this plot, for sure. You
Okay.
just do a spectroscopy, so you
You
just,
just sweep it.
you sweep
then
it, and then you reconstruct this, and then you essentially.
And then you set it there.
Then you set it.
Okay.
For sure, yeah. But that's the calibration part. In actual usage, you're just sending one readout pulse at one frequency.
Yeah, knowing where,
Knowing
where
where
it's at,
yeah,
and then you just wait and collect the data.
for sure, for sure.
What are the like practical considerations for which frequency to select? Beyond just like the difference in the.
Yeah. So this is the transition magnitude. This is just, so this is, if you take, it's the complex signal that you get. And if you take the magnitude of that, this is what I'm plotting here. Daniel Sank yesterday talked a lot about the phase, and his circuit looked a little different. It was a reflective thing, and there the phases of the responses looked different. So apologies for confusing you here. There's just different ways to do readout. In this case, if you have a hanger geometry, you probably want to work with the magnitude. But to answer your question, it's an interplay of magnitude and phase. And in general, we can just actually look at which frequency of your readout pulse do you maximize the separation. So you can form this whole thing while changing where your readout pulse is centered, and the place that gives you the maximal threshold. That's typically how we craft or the maximal separation. That's typically how we calibrate this thing. But it's magnitude and phase. In this case, it's mostly magnitude. Okay, now Daniel also talked about a problem that arises with coupling things to output ports, namely your qubit excitation can leave through that path, right? So in general, your resonator might be here and your qubit might be here in frequency. So if you put ports here and here, basically the path that a qubit excitation would take, then you can see that it really easily leaves the resonator, or really easily leaves here if that photon is at the frequency of the resonator. That's where this resonator sort of becomes like an open. So that would be really bad if our photons, qubit photons, were at this frequency, but they're not. And in fact, at this frequency, they're suppressed, right? They don't leave as easily. So this natural roll off here, this is also a Lorentzian resonance, but if you look through a resonator, not in the hanger geometry, you get this, it's natural attenuation, and this protects your qubit. But this protection is not that big, actually, it turns out. If you put in the numbers, your qubits will be limited to maybe a few microseconds. That's not a lot. So what we do is literally we just slap a second of these on there, an identical copy, basically. And what we get is now a photon, roughly speaking, has to, oh, I'm pressing the laser, has to go through two of these, stop bands. And that is sort of just, it's like take the square of this roll of this function, you get this one. And that's roughly the attenuation that photons will experience, and it's much more. And this protects your qubit, right, from decaying. In fact, this factor, the increase in T1 limit, often turns out to be between like 1,000 or 10,000. Like this method here, as simple as it is, can effectively, for a readout that's fast enough, fully decouple, like fully solve the problem of decaying through this thing here, right? So that's really good. It adds some complexity. And we'll take care of that complexity using ABC matrices. Okay, what it also does is, say you have a feed line and you have multiple of these things, multiple readout resonators coupled to qubits. If you have multiple resonators on one feed line, what you want to do is you want to have them at different frequencies, right? To multiplex, right? Now, if you're driving one of these, to read out, chances are your readout signal might also couple into another readout resonator. You don't want that, right? You might be accidentally reading out a qubit that you never intended to read out because they're kind of close in frequency. Okay.
Question from the online audience: what is a Purcell filter?
Yeah, that's this thing here. It's a great question. I should have said what it is. This thing called the thing is actually a Purcell filter. Is just a second copy of a resonator. So it's also a resonator that's at the same frequency, and it protects your qubit from decaying via the mechanism that I just explained. And this decay through a resonator is often referred to as Purcell decay. And that's why this thing is called a Purcell filter.
Can you design the resonator to be serve as a Purcell filter at the same time?
So are you saying, can we just not have one element that already has a sharper attenuation? That's a great idea. And you should look into that. And many people have, but there's probably ways to improve it. So yeah, there's ways to build, like this is a very simple resonator. You can build more complicated resonators by adding more L's and C's here that engineers shape that looks like this. And then you don't even need a Purcell filter, right? The downside of that is your element becomes more complicated. This is a very simple way to do that. Right? But how to do that is in Posar, right? This is classical microwave engineering, just building filters with steep stop bands, Chebyshev filters, I don't know what kind of filters, like all your favorite filters. They're in that book, so you can just go read one and try to build it, put it to a qubit, connect it with a qubit. But I was talking about readout crosstalk, and this Purcell filter also protects against that. Why? Well, say you're driving here, this resonator here, and that signal also couples, has a harder time reaching your resonator because of this Purcell filter if it's slightly detuned, right? So you can see the difference between the orange and the blue. Maybe at this point you have another resonator drive for a different resonator. And the separation here also quantifies how bad the readout crosstalk is. So all I'm saying is this architecture really does a lot for you, and we want to build it. Now, a little complicated, but if we now look not through the resonators, but what are we actually seeing when we look from the input port to the output port, we see these double resonances here. And that's because we have two modes that hybridize, and they both shift like high. But we can just place our tone at one of these dips, and we can do the same thing there as before. So it's just supposed to be done the same way. Okay. So Nick, I'm just wondering, do we have a break at some point? We can do a break. We can do a break now. Let me see what a good point is. Yeah, so I might just quickly end on this note before we continue after the break, which is now next I would show you how we build this device here using the architecture I just introduced. So this is a semi-infinite waveguide, like this speed line that we talked about, that increases the quantum efficiency. And here we have resonators, but pairs of them each, right? And we multiplex 5 things here. And so this, in practice, can be used to perform really high fidelity multiplexed fast readout, right? This architecture we just talked about. Note that I'm drawing them here as half-wave resonators, but they're actually quarter-wave resonators. Yeah, and so this device has like 25 or so parameters that we need to hit. That's a lot, right? It's not just one frequency, one line width, it's 25 of those things, frequencies and line widths. And so this is where ABCD methods, the one we showed that are computationally efficient and accurate, really shine because they can help us simulate this whole thing in like seconds. So I'll pause there. Just a few questions.
Is a Purcell filter just another mode in the Hamiltonian?
Yeah, so it's just another mode. It's just another resonator, and it's in fact placed at the same frequency as the resonator you already have. Now, in actuality, we build these resonators as distributed resonators, and so it's not just one mode; it's infinitely many more modes. But we can ignore, for the purposes of the qubit physics, for now, we can ignore these higher modes.
You have your coupling teeth kind of in the middle of your resonator, right? When you
Yes.
connect them to each other, wouldn't it be more fair to kind of make two coplanar waveguides and kind of connect them to
At the
the
ends,
middle?
to connect them at the ends, are you saying, or you
So,
should?
I mean, the picture you have on the left,
Yeah.
you connect them at the ends, right?
Yeah.
But wouldn't you in reality have to cut it into two parts and then connect them in the middle?
Yes, yeah, that's what I said. Is this model? It's this is more accurate.
Ah, okay.
I just, to fit them in one row, I wasn't sure how to do it, so I just show them as halfway, but this is the more accurate model.
Yeah, final question. Is the Purcell resonator frequency the same as the readout resonator?
Yes.
Can you explain what would happen if you vary the Purcell frequency away from the resonator frequency?
Yes, stuff breaks. That's what happens. So for instance, what happens is now imagine you have two of these things and you move them away. Your Purcell filter might end up actually choking off your readout resonator. Right? So your Purcell filter is a filter, right? And photons only really go through it if they're resonant with it. You don't want your photons to reach the Purcell filter. What you really care about is for them to reach the resonator, readout resonator. Now, if you want to have an easy time doing so, you choose omega p equals to omega r, such that your photons easily reach your readout resonator. If omega p is very different from omega r, they're filtered by the Purcell filter, and they have a harder time going to the resonator. And so as a consequence, you have to drive really hard, and also your readout will be slower because photons don't couple in as fast. So it makes the couplings weaker and everything gets slower. But
Would it also,
it's workable. It's workable.
would it also like, it also have the same effect of further lowering the curve apathy frequency?
It can improve your qubit frequency. Yeah. So if your Purcell filter moves to the right, for the qubit, what matters is how easily do the photons at the qubit frequency leave through this path. And so for the purpose of the qubit T1, it can be great. It just may mean that your resonator, you have to drive a little harder, that the line width is a little smaller, so readout is a little slower, but it's still workable. At some point, it might break.
It looks like you're designing J to be much larger than kappa in the plot that you showed.
Yes, that's a great point. So in this here, this point, I showed you the line shape, and I said this is what it looks like. It only looks like this if J is roughly equal to kappa p or even larger. How do you see this? The two modes, they're separated by 2J. These hybridized modes. This is only the case when the modes couple together very strongly. And I'll show a few line shapes later where that's less the case, but part of my work is also studying how different ratios of J and kappa P improve the readout. What's the best point for readout? And there's some interesting findings there for sure. Should I elaborate?
Outside the scope.
So really, this is about ABCD methods, and so this is more like a physics question, but I'm happy to elaborate. Just roughly speaking, so this regime here is very robust to variations, and this makes sense. If the modes are slightly detuned, this very strong coupling kind of compensates for that. Like it makes sense intuitively, but if you make your coupling very large, then what happens at this regime, which I find very interesting, is your dispersive shift. Your qubit doesn't really see one mode and then another. It sees two modes that it's coupled to equally, right? So imagine there's like two coupling paths, it's coupled to them equally. This causes both of these modes to shift by chi, right? And you're just using one for readouts, so it's very wasteful. There's a lot of chi here that you're not using for your readout. In the other non-weakly hybridized regime, all the chi is on one mode. So you can be a little more economical with your chi. So those are the most important differences for sure. Yeah.